All right, how's it going? Welcome back to another video here in the series on vector calculus. You might have seen that the section title has changed, and admittedly, this is kind of just a mistake on my part. When I was initially kind of planning out the video series, I had it in my head that much of upper division undergraduate physics courses are based around coming up with solutions to either Laplace's or Poisson's equation. So naturally, kind of containing the videos on Laplace's equation and on Poisson's equation, the original intention was, yeah, we'll just throw them in with the physical applications and that'll be good. But as I've been kind of going through the videos, actually recording them, it really seems like the focus and the way that I'm thinking about this in my head is just looking at how we can apply vector calculus to Laplace and Poisson's equation and their solutions, as opposed to motivating them with physical examples like what we were doing with the applications to gravity and applications to electromagnetism videos. That's not to say that what we're doing right now does not apply to essentially anywhere where you can apply those equations. They have many physical applications, but it just seems like it would make more constructional sense to have our own section for it. So really, I guess I'm writing a new section, but really this probably should have been the section title a couple of videos ago. So to make sure that we understand how we should be sort of organizing this, compartmentalizing this in our heads, we can go back 2 videos ago where we said, let's just introduce what Laplace's and Poisson's equation are. And essentially, it is a partial differential equation which involves second order derivatives of a function. And I already have a lot of stuff on the board, but let me just write something here. If we had a function phi of x, y, and z, Laplace's equation more or less involves the second order derivatives of this scalar function, not including the mixed partial derivatives. And really all we did in that kind of first video on the spherically symmetric solutions to Laplace's equation was kind of the obvious, or I don't want to say obvious, but maybe once you think about it, it naturally makes sense that if you have a function of multiple input coordinates, if this function just doesn't happen to depend on all of those input coordinates but one, now your equation, your original partial differential equation, will reduce to an ordinary differential equation, and then use standard methods from ODEs to solve Laplace's or Poisson's equation. And that was kind of the idea in that video. Then in the most recent video, and I guess now this is what I have here on the board, what we discussed was not so much, properties of the solutions to Laplace's and Poisson's equation, but rather we were looking at theorems, specifically the uniqueness theorems, regarding the number of solutions to this equation right here. And just so we're aware, and we're probably already familiar with this, but whenever I refer to Poisson's equation, those same statements should apply to Laplace's equation, because Laplace's equation is just the special case of Poisson's equation where you have a zero right-hand side, right? And that's what we were doing in the last video, where we were saying if we have a function phi, and let's suppose that we want to find the value of phi on the interior of this volume right here. And we don't have the value of phi on the interior, that's what we're trying to find. But we know that if you take the Laplacian of phi and it's equal to some density distribution defined on this volume, kind of that being the first piece, and then the second piece being that you know something about the boundary of this volume, or more specifically, you know information about your function phi on the boundary of this volume. And we went through these 2 specific cases, right? One instance is if you knew the value of phi explicitly on the boundary, and it was equal to some scalar function, and we call that a Dirichlet boundary condition. In this specific case, if a solution is going to exist at all, then there's going to be one single solution. The solution is going to be unique. Then in this case here, we don't know the value of phi on the boundary, but we know the value of its derivative on the boundary. So in this case, where we have Neumann boundary conditions, we said that if a solution does exist within this volume right here for Poisson's equation, then it's going to be unique up to a constant, which means that if your supposed unique solution is phi, just being the solution to the equation, right, then phi plus c for any constant c would also act as a solution. And that's kind of what we were talking about in the last video. What are the number of solutions to Poisson's and therefore Laplace's equation, right? But notice that in saying the number of solutions, that in itself doesn't say anything about the properties of the solutions. We're just saying if a solution exists, this is how many exist, right? So what we're going to be doing now in this video and then the upcoming video is to say, okay, we have an idea for how many solutions should exist for a given setup. What are the properties of those solutions? Without having to go through actual methods that you would learn in a partial differential equations course. Within the realm of vector calculus, what can we say about the solutions of Laplace's and Poisson's equation? Okay. So hopefully that makes sense, and that's going to be the direction that we're going here. Now, this is kind of the first of those two videos, and the first of those two videos is going to be covering properties of solutions to Laplace's equation. And then you can probably guess what the next video is going to be about, right? Properties of solutions to Poisson's equation. So what I'm going to do here is just to introduce some terminology. I don't normally do this by having a definition before I've written anything else down, but this terminology is going to get used throughout the video, so I just want to introduce it now so we can just use it going forwards. There's this type of function known as a harmonic function, and a harmonic function is just a specific solution which satisfies Laplace's equation. So if you have just any function phi, that may or may not be harmonic, but in the case where you know that the Laplacian of this function is equal to 0, then we call that function a harmonic function. Okay. So hopefully that makes sense. This is just what we call a harmonic function, and we want to be specific here. We want to make sure that we're careful here. A solution to Poisson's equation, where you have this non-zero right-hand side, not necessarily going to be a solution to Laplace's equation, right? In fact, in general, if phi satisfies Poisson's equation, that means the Laplacian of phi is some non-zero quantity, right? Whereas a harmonic function is specifically where the Laplacian of that function is equal to a 0 right-hand side. So what I'm trying to say is that what we're going to be working with in this video specifically are looking at properties of functions which specifically satisfy a 0 right-hand side, specifically Laplace's equation and not Poisson's equation. Okay. So hopefully all of that makes sense. And the first thing that I'm going to do is I'm going to, erase what we have here, and then we're going to write out the first property for these harmonic functions called the mean value property, and we'll unpack that together. All right, so we have the first property of harmonic functions up here. It's called the mean value property. It's an interesting one, so let's go through it together. It says here that we're going to define a harmonic function f of r on a volume V, which contains a solid sphere, kind of parameterized by this equation right here, with a boundary S defined like this. We're then going to be defining some quantity being the average of our harmonic function, and ultimately what the theorem claims is that the average at the boundary of our sphere is equal to f at this value a, which is the center. Now, there's a lot going on, so I want to make sure we understand what this is saying before we go through proving it. So just through the first part, let f of r be a harmonic function on V. What that tells us is that if we have some volume V, then if f of r is a harmonic function, then we know that within this volume V, that nobelus squared of f, or the Laplacian of f, is equal to 0. The reason why I'm not calling the harmonic function phi will be kind of apparent as we go through the proof. It's because we're going to end up using spherical coordinates where phi is one of those coordinates. So I'm calling the harmonic function f. But the fact that f is harmonic means that within this volume V, now the Laplacian of f is equal to 0. Now, it says that within this volume V, this volume contains a solid sphere given by this equation right here. So what that means then, I'm just going to erase this. Hopefully we know that within the volume V, nobelus squared of f is 0. What they're saying that you could have this volume, and within this volume you could have an overall sphere, which I will do my best to draw like this. So we have a sphere, and it's given by this equation right here. And essentially what this means is that they're going to define this vector A to be the center of the sphere. So that's just this point right here. But this is a point in 3D space, so it can be represented by a 3D vector A. And the fact that the sphere is all the points less than or equal to a value r tells us that the radius of this sphere is r. So maybe what I'll do is I'll write up here that the center of the sphere is the point A, and then the radius of the sphere is that uppercase R value. So that's just what they're saying right here. It has a center A, a radius R, and then this is almost redundant information. This is a sphere, and the sphere has a boundary, and the boundary is the set of all points R whose distance from A, so the distance between a point and A is radius R, right? And that's kind of just saying all the points on the boundary that make up the spherical shell are a distance uppercase R from the center point A. I realize that that's starting to get cluttered, but that's just what that's saying right there, and center and radius. Now, assuming that makes sense, that's just kind of the setup. And what they're saying next is, let's define some quantity f bar of r. And f with a bar on the top of it, typically, and in this case, it refers to the average value of f. So I want to make sure that we just understand what this is saying. The average of f, what this quantity is saying is this is the average of f at a radius r. So this is the average value of our harmonic function on the boundary of the sphere. So it's not within the sphere where it could have any radial distance, little r, but this is specifically at the radius on the outer shell, and that's why we're evaluating it at uppercase R. Okay. So this is supposed to represent the average value of the harmonic function on the boundary of the sphere, and hopefully this kind of makes sense. What we're doing here, we have this prefactor out front, but then we have this surface integral, and the surface integral is over S, and S is just the boundary of this sphere here. So I want to make sure that we're not getting these things too mixed up. The overall generalized volume is V. The overall boundary of the volume is just the boundary of V, like this. The boundary of the sphere, though, is different than the boundary of the volume. The boundary of the sphere is S. Okay. So what we're doing with this function is we're integrating over S, integrating over the boundary, over the boundary of our sphere. And what we're doing is we're just adding up the value of our harmonic function, this function f, over the boundary. So you add up over the boundary, and then you divide by the surface area of the sphere, right? And the surface area of the sphere is 4 pi r squared. So this is just saying the average value of this function on the boundary. I want to make sure that we're not confusing this somehow with the flux of this quantity, because it might look like that. We see this integral, and we have a function integrated over S. Want to keep in mind the flux applies to when we're integrating a vector value, a vector valued quantity, a vector field, right? And we're adding up the normal components of that vector field over the boundary. That would be the flux of a vector field. But in this case right here, the function f is itself a scalar function. Notice that we don't have an arrow over f. Admittedly, this looks kind of confusing because we have a bar over f, but f is a scalar function, so it doesn't make sense to be talking about the flux of a scalar function. So this is not the flux right here. This is just the average of this quantity. All right. So hopefully that part makes sense too, because that can be a little bit confusing. So we have a lot of setup. Ultimately, what we're saying is that the average, we define this quantity, which is the average value of the harmonic function on the boundary. What the mean value property is actually saying is simply the short statement right here. So assuming we got all of that, then what it says is that the average value of our harmonic function on the boundary is equal to the value of the harmonic function at the center. Okay? And that's why we have this mean value property. Basically, they're saying that if you were to pick any point within this volume, in this case it's the point A, and you can almost do this in reverse, right? If this is your volume, if you picked a value A right here, and then you wanted to find what is the value of your harmonic function at A, then a way that you could compute it is by this. You could form a sphere around this point. You could form a sphere around A, something like this, and then add up the value of your harmonic function over the boundary of the sphere, and they're going to be equal to each other. So the value at the center is the average value over the entire boundary. That's why it's the mean value over the boundary. So they call it the mean value property. Okay. So there's kind of a lot of pieces, but hopefully that makes sense, that the value on the outer edge is equal to the value in the center. So we're going to now go through proving this, because that's what we got to do, right? And what I want to first do to kind of start this proof off, let me just write proof here, is that hopefully it makes sense that in the limit as r goes to 0, this equation should naturally be true. And let me explain why. So we have an overall generalized volume, but let's say we're now focusing on that sphere contained within the volume. So we have this sphere, and the center of the sphere is A with a little vector sign. Let's make that a little better. A with a vector sign, and the radius of this sphere is r. Okay. So this is the setup. This thing is contained within our generalized volume V. And hopefully it makes sense that if you were to take the average value on the boundary, on this spherical shell, but then you were to do something else. You were to shrink this spherical shell so that it gets closer and closer, it gets progressively smaller. You're shrinking the value of r. As it gets smaller and smaller, it's going to get closer and closer to just the center of the sphere. And in the case where it gets infinitesimally small, it's going to get infinitesimally close to the center of the sphere. So what we can say is that we do, I guess we're not going to formally prove this, but hopefully it just conceptually makes sense that in the limit, as the radius of our sphere gets smaller, then we would say that the average value equals f of A, right? And we're going to kind of hold on to this fact until the very end. But that's just a property that hopefully makes conceptual sense, right? If you shrunk this sphere, it's going to get progressively close to the center, and then the average value over that sphere will eventually just be the value at the center. Right. Now, assuming that makes sense, let's hold off on that, and we'll use that at the end. So what I want to do now is just to imagine this, or just to take a look at this area element right here, ds. Right now we're integrating over the surface of this sphere, a spherical shell. And naturally we want to be using spherical coordinates for this, right? So ds is going to be written in terms of spherical coordinates. And we just have to ask, what are those spherical coordinates, right? And along the surface of the outer surface of the sphere, like we mentioned, all the points are going to be a constant radial distance from the center. All of the points on the surface are going to be a distance uppercase R from the center. So the radial coordinate's going to be constant. It's the angular coordinates that are changing. So we can write our ds element as this r squared sine theta factor. And this is kind of the determinant of the Jacobian. We've seen this factor kind of show up before. That's where it's coming from. But then I'm just going to write d theta, d phi, where theta and phi are the two angular coordinates and spherical coordinates that we're integrating over. Okay. So this is the area element, ds here. And what I can do is I can just divide r squared over to this other side, like this. So I have ds over r squared is equal to this expression. And by doing that, notice that the resulting expression, ds, this fraction here, ds over r squared, it's equal to this right-hand side. And now this right-hand side no longer depends on r. Why? Because we divided it over, right? So hopefully that kind of makes sense. And the fact that it doesn't depend on this radius here, r, is going to be important. Because the next thing that we're going to do is we're going to differentiate both sides of this averaged value with respect to this radius right here. And that might seem like kind of a weird step to be doing, or it might not make sense, at least immediately why we're doing that, but it'll make sense by the end. So what we're going to do now is we're going to take this this definition for the average value of the harmonic function at the boundary. We're going to differentiate it with respect to r. And specifically, I'm referring to the radius of the sphere. Okay. Now, what we can do here is we're going to differentiate the left-hand side. We also need to differentiate the right-hand side. All right, so we need to take ddr of this whole thing. So let me write this out here. We have 4 pi r squared, 1 over that, integral over s, then we have our harmonic function ds, like this. Okay. So this is what we're integrating over. And maybe just in case this part is confusing, because r is just the radius of this sphere. It should be a constant value. So it might look weird that we're integrating with respect to a constant. So just to be clear here, and I'll write it up in this corner, this notation ddr, like this, simply refers to differentiating with respect to the radial coordinate. And then once you've performed that derivative, then you set whatever the value of little r is to be the radius itself. So that's just what this symbol refers to. Okay. So that's kind of what we have right here. And what I'm going to do now is I can look at this expression out in the front, and I have 4 pi r squared, and all of these values are actually constant, right? 4 and pi are constants, but the radius of the sphere is also constant. So I can bring a constant into the integral, and that's just what I'm going to do. I'm going to bring 1 over r squared into the integral, and I'm going to conveniently place it over ds. Okay. So it looks like this. Now this is where we use this fact right here, where we said that ds over r squared is just this expression. This expression does not depend on the radius of the sphere or really any radial variable. So now looking at this derivative right here, we're taking the derivative of 1 over 4 pi. Well, that's a constant, so that can be brought out to the front. Let's evaluate this derivative now. 1 over 4 pi is a constant. It can be brought out to the front. Then we have the integral over s. Then we're going to differentiate this expression and this expression, this product of two things within the integral. But we said that ds over r squared doesn't depend on a radial coordinate. That's what this thing is right here, right? So the derivative acting on this quantity is actually itself a constant, meaning that this derivative, d of dr, only acts on the harmonic function f of r by itself. So all of that is to say that by evaluating this derivative, what we're really getting is df, the derivative of our harmonic function, and instead of writing d uppercase r, I'm going to use this definition right here. I'm going to use df d little r, differentiating f with respect to the radial coordinate, and then defining the radial coordinate to be the radius of the sphere. And then we still have, I guess, ds over r squared out in front, because that's a constant with respect to the radial coordinate, right? So kind of an interesting thing. All of that is to say that this is the only thing that the derivative acts on right here. Okay. Now the next thing, and this is where the fact comes in, that we are working with a spherical geometry specifically. Because if you remember in the setup, we had some generalized volume that just contained a sphere. So the question is, well, why is sphere specifically, right? And it's at this point where we're going to make use of that. So another way of expressing df dr, maybe I'll write it up here. Way of expressing df dr, it can be evaluated at the radius or whatever, but primarily this derivative right here is that we could also express this as the gradient of f in a dot product with r hat. The r hat, the radial unit vector, the one that points radially outwards. Okay. So the way that you could see this too, by the way, is if you were to write out the gradient in spherical coordinates, the generalized gradient, and put that in a dot product with r hat, this is just what you would end up getting right here. So this derivative can be re-expressed like this, but not just that. Because we're working with a sphere specifically, or we're integrating along the surface of a sphere, r hat has a special name. R hat's always going to point perpendicular or orthogonal to any point on our surface. So it is true that this derivative can be expressed as the gradient dotted with r hat, but it can also be expressed as the gradient of f dotted with n hat. The radial unit vector happens to be normal for this specific geometry right here, because we're working with the sphere. Okay, and that's going to become important in this expression right here. So I'm going to rewrite this equation. I have df dr, or d average f with respect to dr, like this. In case we're wondering, why aren't we just using lowercase r? That will become apparent later as well. But there's a reason why we're differentiating with respect to upper r, or using that definition for a derivative. So this is our left-hand side, and that's going to be equal to 1 over 4 pi, and the integral over s. And now I'm just going to rewrite the integrand. Instead of df dr, ultimately evaluated at the radius, I'm going to re-express it here as delta f, or not delta, excuse me, del f, the gradient of f, in a dot product with n hat times our ds over r squared quantity. Okay. So that's the current expression that we have. Now, again, putting this 1 over r squared factor here in the first place was just to make use of the fact that the derivative would only act on the integrand and not the area element explicitly. Or actually, it would act on the f function, the harmonic function, and not the area element, right? But r is still a constant. It's just the radius of the sphere. So what we can do is just like we could incorporate it into the integral, we can also take it out. We can do that with constants, right? So that's what I'm going to do. I'm going to take this r squared value and put it back out in the front, and we'll see why I'm going to do that. So now the prefactor is 4 pi r squared, and then the integrand is the gradient dot n hat times ds. Okay. So hopefully that makes sense up until that point. Now, the reason why I did that is because hopefully this looks very familiar. N hat times ds, or the unit normal times the scalar area element, is just another way of writing the vector area element, right? We're making use of the fact, I'm writing all over the board now, but we're making use of the fact that n hat ds can be written as ds, like this. So if I just rewrite this, now I can re-express this as the gradient of f in a dot product with this area, or this vector area element, excuse me. And now at this point, that subtle thing that we were saying over here, we said this was not the flux, because f of r, the harmonic function, is inherently a scalar function. Well, now let's look at what we have, right? Because we have a scalar function, but we're taking the gradient of it. And when a gradient acts on a scalar function, we get a vector function. And what we're doing is we're taking the normal component of this vector function and adding it up over the surface of some volume, and it's a closed surface. So while this expression right here was not the flux of f, because you can't have the flux of a scalar function, you can have the flux of the gradient of f. And now in this case, that is what we have. We have this quantity right here, let's underline it, this is the flux of this vector function, gradient of f, right here. So we can kind of make this connection here that now we've been able to rewrite the integral as a flux integral, and it's at this point where we will make use of the divergence theorem. That was a tongue twister, where we will. Try saying that 3 times quickly, all right? So let's make use of the divergence theorem for this specific function. I'm going to have some prefactor out front. This won't end up being too important. Let's just focus on this integral for a second here. We have the integral of s, which is really the flux of this vector field right here. And the divergence theorem tells us that rather than expressing the flux of this vector field, we can write out the flux density, or the divergence of this vector field. So let's take the divergence of this vector field, which is gradient of f. And then this is the flux per volume, and then let's just integrate it over the volume. dv. What I think I'll call this dv prime and v prime. The reason why I'm calling it a prime is because we already said our general volume was v, that happened to contain the sphere, right? So v prime is the volume of the sphere with surface area S. I don't want to put v here because that makes it look like we're integrating over the general volume, when we're really just integrating over the volume of the sphere, and those are 2 different things. They could be the same thing, but in general they're not the same thing. Okay, so that's why I'll put v prime there. All right. So what we're doing now is this is the flux over the surface of a sphere. It's the same thing as the divergence, or the flux density of this quantity integrated over the volume of the sphere. So maybe let's even put this. We'll say that v prime is volume of sphere. To not get it confused with this general volume v. So this is just a result from the divergence theorem. Now let's look at what the integrand is on this integral right here, right? We have the divergence of the gradient of f. Another way of expressing this, the divergence of the gradient of f. We can say that this quantity right here that I'm underlining is equal to the Laplacian of f. Okay. And now it's at this point where we make use of the fact that f is a harmonic function. Remember at the very beginning, we said let f of r be a harmonic function on some volume. So this is a harmonic function, and by definition, any harmonic function satisfies Laplace's equation. So I'm writing a bunch of things, but we don't need this anymore. Because f is harmonic, that tells us that the Laplacian of f is 0. Now, the Laplacian of f is 0 on some generalized volume. Right here, we have the Laplacian of f specifically on the volume of the sphere. But remember, the sphere is contained within the generalized volume. So if the Laplacian of f is 0 on the generalized volume, it's got to be also 0 on any subvolume or subset of that volume. So what we've ultimately come to the conclusion is that this integrand is 0, thus this integral and this integral is just 0. So all of this is, this all equals 0. So if this is 0, that's just what we had right here, right? We said this is the flux of this vector field, but we now concluded that it's 0. So the ultimate, or one of the ultimate, what we've been trying to get to is trying to come up with an expression for the derivative of the average value of the harmonic function with respect to this, this radius. And what we found is that the derivative is 0. Let me write that out specifically. We have now that the derivative of the average value with respect to the radius is 0. It's now at this point, we might be saying, okay, sure, we found a derivative at 0. How does that prove, though, ultimately, that the value of our function f at the center is equal to the average value on the boundary? And now we're gonna be able to connect all the dots here. So what this derivative is telling us, and this is why we use this uppercase R notion for derivative, is that if we were to look at the average value of our harmonic function, and we were to see how does the average value of the harmonic function change as we change our radius, basically the fact that it's 0 says it doesn't change. So what that tells us is that, let's try to draw the overall picture here. This is our generalized volume. If we had a sphere of radius r, the average value of f at this radius right here would have some value, right? Now let's suppose we change the radius. Let's make maybe a smaller circle. Now let's make a smaller circle with radius r. What's the average value of f now? Well, it's also the same. Why is it the same? Because the derivative is 0. And then we could make it even smaller, right? I don't know if we can even see that, but it's supposed to be a smaller circle. I'm not even going to try to draw the radius thing anymore. That's a smaller circle. Hopefully you can imagine that as you take your sphere, you progressively make it smaller. The average value of your harmonic function doesn't change. So you can make your sphere smaller and smaller and smaller, and this quantity is going to remain the same. And it's now, so hopefully that makes sense. And it's now at this point where we can make use of this fact, where we or this thing that we kind of assumed, but hopefully it conceptually made sense, right? In the limit, as your radius shrinks to 0, you're going to get to the value of your harmonic function at the center, right? If you took your radius, shrunk it down to just a point, you would get the value of f at the center. Well, it doesn't matter. What this derivative is telling us is it doesn't matter how much you shrink it down. You can shrink it down as much as you want, including shrinking it down in the limit where r goes to 0, and it will still hold the same value. So in other words, I don't know where I'm standing. The value of the function, the average value of your harmonic function at any radius r, ultimately can be shrunk down to a point and will ultimately equal the value at the center. And that's how you prove the mean value property. Okay. So a lot of little clever arguments in this one. This is a fun one to go through. So hopefully that makes sense. If there are questions on this, please leave a comment. I'm happy to try to answer any of these steps here. So this is the first, really, with all of this, let's put a box around something. This result, if you were to have some sphere within your volume has a radius of r, then the average value of a harmonic function, which is what we're interested in, is going to equal the value of that harmonic function at the center of that sphere. So that's the first property. Now, the next property that we're going to work through involves understanding what local minimum points and local maximum points are. We probably already have a decent idea with what they are from single variable calculus, But I want to first just go through the definition just to make sure that we have kind of the formal-ish definition in our head, and then we'll go through the next property after that. Okay, so we have the definition here for a local maximum, so let's go through it together. It says here that the function g of r has a local maximum at r equals a if for some parameter epsilon, which is greater than 0, we're going to have this condition where g of a is greater than g of r whenever the distance between r and a is less than epsilon. All right. Now this looks probably like a very complicated looking definition because we're probably used to this idea from single variable calculus that if you have some curve, right, the local maximum is the highest point. Excuse me, the local maximum is the highest point on the curve, right? And it turns out that this definition here is saying the exact same thing, but it's just using some more formal language or some more formal mathematical symbols. So let's try to understand how these symbols convey the same idea. So with this picture that I'm going to draw here, let's suppose that our function g of r, by the way, the reason that I chose to call the function g and not f, for example, is because we used f to be a harmonic function in the last whiteboard. I want to make it clear that this local maximum idea can apply to any function and not just a harmonic function. So I'm just calling it some function g. Now let's suppose that our g function is a scalar function of 2 dimensions, x and y. Okay, so we could draw a xy plane down here, and it's like this flat. Maybe we even call it xy plane, like this. And this curved value then that kind of turns this 2D flat plane into a 3D picture. This curved is the value of our function g at a given value xy. And hopefully this will become clear as we go through this. So first thing, it says that our function g, and maybe let's even label this curve is our curve g of r for any value of r. Now it says in this example, g of r has a local maximum at r equals a. Now r, this position vector r, we're just writing to be x comma y. So what we could do then is we could say that when we have r equals a, we think of this as x comma y equals a. So this a quantity right here is just a vector in our 2D space. And maybe we'll call it's at this point right here. This is our 2D vector a. If we want to be very explicit with this to make that clear, maybe we can say it has an ax component and an ay component. Right? So we have some point in the plane. And we're saying it's at this point where our function is a local max. Why is that the case? Because at this point, a in the plane, the corresponding function g evaluated at a takes us up to this top point right here. So if this is a, this is the value of our function at a. Okay, so that's kind of how this picture reads. So we're saying that this function has a local max at r equals a. And here's the condition. This is the part that we're going to try to understand. It's saying if for some epsilon greater than 0. Now, epsilon is a parameter that we usually take to be a small positive number. And we see this a lot in courses like real analysis. But in this case, I mean, they can be true in this case as well. But we're just going to take it to be some positive number. And what it's going to do is it's going to define a neighborhood or a collection of 2D points around this vector value a right here. So to make this kind of clean and not get too cluttered, I'm going to erase that notation for now. We can see this is all in the xy plane, but I'm going to define a neighborhood kind of like this. I'm going to draw a 2D circle in the xy plane, and the radius of this 2D circle is going to be defined by this epsilon parameter. So now this dashed line that I or I should say this dashed circle that I drew, now provides a collection of points contained within a radius epsilon. So this is a neighborhood of points within our that includes this vector A right here, and A is going to act as the center of this circle right here. So it's saying for some value of epsilon greater than 0, that's what epsilon defines. It defines a neighborhood around our value A. But now let's just see what are all the possible, because there are a bunch of points in this circle, right? There's this point, this point, this point, this point, and I can just fill in this circle with a bunch of individual XY data points. What do those XY data points look like now along this curve, along this function G? Well, what we do is we just kind of extend this upwards, and then this circle in 2D space. Now within this, now when we evaluate G for all of the data points within this circle, it's going to map out the top edge of this curve right here. So if we can imagine this is kind of like an egg-shaped thing, the top of an egg, we're cutting it at this circle right here. And all the points that lie within this circle and above are the values of these points in the XY plane when you act G on any of those given points. Okay, so that's what epsilon is right there. It defines the 2D parameter, but then to see how we go from this 2D case to this 3D case, that's this part of the statement right here. Now it's saying that G of A is greater than G of R for any value of R, as long as the distance between R and A is less than epsilon. So there's a lot of stuff going on there, but let's try to understand it, okay? Basically, they're saying G of A is greater than G of R. So let me just put another point right here. Maybe we'll call this G of R1, for example. Maybe we'll call this point G of R2. Like this. And what they're saying is that G of A is going to be greater than G of R1 or R2 or G of R anything, as long as the distance between R1 and R2, the distance between any point in A is less than epsilon. The idea, this quantity right here just says as long as whatever your value of R is, whether you call it R1, R2, or whatever, as long as it lies within this neighborhood centered at A with radius epsilon. So this point would be probably this point right here. This would just be R1. This point, G of R2, probably goes down to right here. This point is R2, like this. So basically they're saying as long as the distance between this point and the center is less than the radius, then what we see is that the value G evaluated at the center is going to be greater than this thing right here. So it's kind of this formal way of describing it, but this is the, I just bit my tongue. This is the visual picture to describe what's going on. All right, to say that this mathematical framework just describes this picture that we're already familiar with, right? This is all from Calc 1. Now, the last thing that I want to quantify or to mention is that with this local maximum idea, or two things. First is that with the local maximum, this is true for some value of epsilon. Notice that we're not saying that this needs to be true for all values of epsilon. As long as you can define some value of epsilon, you have some neighborhood that you're working within. If you were to generalize this and say that not only does G of A need to be greater than G of R for all epsilon, in other words, this circle in 2D space can be any size, it's in that case where you don't have just a local max, but you have a global max. Okay. So the fact that you can just pick some epsilon says that that's what causes it to be a local max. The idea for why it's some epsilon too, and just you're saying one specific value of epsilon, is because let's say that your function, your G of R function that looks like this curve right here, let's say it does something like this. We're ultimately this point up here is higher than this point right here. If you were to pick epsilon, the radius, so that the radius extended out to here, you pick epsilon to be this big, this point is no longer the local max, because this point is higher than here. G of R is now greater than G of A, right, if you extend it out to here. So by saying for some epsilon, you're just saying that you can pick some neighborhood where this is the highest point. Not saying that it need, but that doesn't guarantee it's the highest point if you pick a larger neighborhood necessarily. Okay. So that's kind of the first point. And then the second point is that this is just the definition for a local max. The local minimum definition would have the exact same structure. The only thing that would change within this definition, if we were to do this for a local min, is we would write G of A is less than G of R. And you kind of just invert this picture. So rather than having like the highest point on a hill, you'd have the lowest point in like a valley, right? And then the framework, the rest of the definition should still apply. So that's a local max. And sorry if that took a while, but we're going to use this notation here. I want to make sure we understand it, because we're going to use this notation in the next property, and then we'll call it at that point. Okay, so we have something here called the maximum principle. This is the second of the two properties we're going to look at for harmonic functions. So let's go through it together. It says here that if we have a function f and it's harmonic on a region V, some volume V, then f cannot have a maximum, whether it's a local max or a global max, it can't have any maximum at an interior point, which we can call A, within the volume V. Now, really quickly, this is the maximum principle, but an identical concept you can talk about is the minimum principle. It'll just be a matter of switching inequality signs ultimately. But let's try to first understand what this is saying right here. So we have some region V that we're going to work within, call this V, and it says here that f is a harmonic function within this, or on this region right here. So that tells us that the Laplacian of f is 0. Laplace's equation is satisfied. Now, what it's saying here is that it's not referring to Laplace, the Laplacian of f. This statement is referring to the function f itself. It's saying f cannot have a maximum or minimum. So what we're saying then is that suppose Laplace's equation is satisfied within this volume, and then suppose that using techniques of PDEs, you were to solve this, and then the solution is f equals something, right? Then what they're saying is that if you were to plot out f, what is the value of f for the points within this volume, then this function f, the solution to Laplace's equation, would not have a local max or local min within the volume. And that's what we're going to prove. Okay. Now, to do this, we're going to use a proof by contradiction. Let's suppose somewhere within this volume, and I'll start out maybe over here, this little dot. Let's suppose that we do have a local, we'll work with the local max, but this could be a local max or min, right? Let's say it's a local max. And yeah, we'll say A is a local max. Now, so let's start with that. We'll say let, or not A, I should say, but f of A, let f of A, because we're looking at the value of the function at different points, right? So f evaluated at this point be a local max. And we're going to eventually show that this is an incorrect assumption to make in the first place, that this has to be proven wrong. So we're going to disprove this. So we have this local max point right here. And what that means, based off of the definition that we had in the previous whiteboard, is that f of A, the value of the function at this point, needs to be greater than the value at any nearby point, as long as this nearby point R is within a certain neighborhood of size epsilon, right? So we said where 0 is less than R minus A, less than epsilon, right? Basically saying it's within the neighborhood of radius epsilon centered at A here. Now, the next thing that we're going to do is we're going to make an argument that we didn't explicitly state in the last whiteboard, but hopefully it makes sense. That we saw that you would have a local max for some neighborhood epsilon, but it wasn't for any neighborhood, right? Because we saw that if we made epsilon larger, that led to the possibility that maybe there was some point farther along in the parameter space that was larger than our local max, right? So we couldn't make epsilon larger. But what we could do is we could make epsilon smaller, and that would still be allowed, right? Like if we had a neighborhood of radius epsilon like this, and we had like that curve where f a value, and this is A, this is the center where our local max was located, right? And it was kind of like this positively curved function right here. We could also draw a smaller neighborhood, and the same statement would be true. If we had a local max within this region, we're going to have a local max within this region. So that's what we're going to do. We're going to define not an original neighborhood epsilon. We're guaranteed to have an original neighborhood epsilon just by f of A being a local max. But let's define a new neighborhood of radius delta, where specifically delta is going to be a smaller number than epsilon. Now, this is practical for a couple of reasons. One just happens to deal with the fact that let's suppose your local max location is located at A, right? Let's suppose this location is only kind of close to the boundary of our volume. I purposely tried to draw it near where this curve was, right here. So if we were to define a neighborhood epsilon, we can define a neighborhood epsilon however we want, right? It's not like this is the only volume that exists. There's like all of R3 exists, but this is the volume that we're working in where Laplace's equation is guaranteed to be satisfied. We could define a neighborhood like this, but the problem is what happens if this neighborhood extends out the other way? What happens if we tried to draw it out like this? I try to draw those equidistant, right? Then all of a sudden, this neighborhood that we're working within no longer is completely contained within the volume or the region V. And what we like to do is we like to define a neighborhood small enough so that no matter how close our point is, or no matter where it is, even if it's very close to the boundary, we can always draw a neighborhood that is completely contained within the overall volume. So what we would do in this case, if this is where our point is, we might draw a neighborhood like this. So it's just like a little error bar. I don't even know if we could see it. But this neighborhood, it's smaller than that starting epsilon, but maybe we draw it small enough so that this entire region is contained within the overall volume. And that's how small delta is going to be. So how small is it? Small enough so that the entire neighborhood is contained within V. Okay. Now, that is one practical purpose for why we're defining this, is to ensure that the neighborhood is contained within there. Another one is so we can make stricter statements relative to this. So this is true just because f of A is a supposed local max. We're going to show that it doesn't exist, but it's a supposed local max. Now, if we define this new neighborhood, delta, then in this neighborhood, I don't know why that's tough for me to say, but then we would have this statement, f of A is still greater than f of R, but now rather than saying 0 is less than R minus A is less than delta, rather than saying this, I can replace this less than sign with an equal sign, right? Hopefully this makes sense. If I had a starting neighborhood epsilon, and this was true for all of the interior points within here, then if I drew a smaller neighborhood, then I wouldn't just have to restrict this inequality being true for all the interior points within here. I could also include it in the boundary, right? Because this boundary is contained within the overall larger boundary which we originally defined. So I can replace this less than sign with an equal sign, and we'll see why that's important in a second. Okay? But that's going to be kind of the other practical purpose of having this smaller neighborhood parameter delta. You can replace the less than sign with an equal sign. Now, one more thing that we can do, we're saying here that within this new smaller neighborhood delta, f of a is going to be larger than f of r at all points on the boundary. Again, this is the collection of points whose distance from the center is equal to the radius. If I were to draw out my neighborhood A with radius delta, this is making a statement not about the points interior to delta, but the points whose distance are equal to delta. This is making a statement about all the points on this closed curve that I drew out here. And then I guess if we're working in R3, V is a three-dimensional volume, this wouldn't be just a 3D surface or a 2D surface, this would be a 3D sphere. It'd be a spherical shell of it'd be a spherical shell of radius delta. Let me even try to draw that a little better. So we have in 3 dimensions, we would have a 3D neighborhood as opposed to a 2D one like in the previous whiteboard with radius delta. And this statement would be true for all points on the boundary of our sphere, here, our 3-dimensional neighborhood. We might see where this is going at this point. Okay. One final thing that we're going to do is we're going to say that if this is true, if the value of f at the center is greater than all the points at the boundary, then that would imply that the value of our harmonic function at the center is greater than the average of those points, at the boundary. We're using notation from the mean value theorem, right? And what this is saying too is let's just put some numbers on this to hopefully make this concrete. So let's say f of a is, I don't know, 30. All right. And then f of r is the collection of points on the boundary, distance delta away from this 30 point. And maybe those are a bunch of numbers between, I don't know, 0 and 10. So we have 0, 5, 6, 8, 3, whatever, right? This is a case where 30 is greater than all of these numbers. And if 30 is greater than all of these numbers, it needs to be greater than the average of those numbers, too. That's all we're saying in this subsequent line down here. It's a more mathematical way of saying it. That's all we're saying, though. Okay. So then this would have to be true if there's a local max. But then it's at this point where you contradict the mean value property, because the mean value property says that if you have a volume and you can define a sphere within that volume, which is what we did, that's why we defined delta, then the value at the center should be equal to the value at the average value at the boundary. But we see that this isn't a greater than or equals to sign. We never had this. This was always a strict inequality sign that originally came from this part of the definition for the local max. So there's no way that this can be true in the mean value property being true. So therefore this is wrong, and therefore our original assumption of f of a having a local max within V was also incorrect. Okay. And that would prove the maximum principle, and by similar logic, the minimum principle. Okay. So yeah, those are the two properties that we're going to cover. I feel like this video has gone on long enough, but yeah, hopefully that was enjoyable to watch. We were able to understand everything, and I'll see you in the next one.